Hello friends, this video on S block elements part 2 is brought to you by examfear.com. No more fear from exam. Let's discuss the periodic table trends. We have already discussed this in the last few chapters, but this is critical for understanding the alkali and alkaline behavior. So let's discuss this once again. So let's first talk about the atomic radius. So we see that if you go down the group, the atomic radius increases. We have seen this the moment you go down a group, the number of orbitals shells increase and thus the radius increase. So we'll discuss more about up and down trend here because these trends are not required for us, at least to understand in this chapter. If you talk about electronegativity, what is electronegativity? Electronegativity is nothing but ability of an electron or atom to pull external electron. So if you see here in this case, the moment you go down, right, the nucleus is away from the surface, right? So the distance is increasing, so the ability of the nucleus to attract external electron is decreasing, right? There will be a extra electron E here and one more extra electron here. So lithium will be able to attract all the more with more power, right? Because the distance is less. But here if you see the distance is already more, right? So if we talk about this more, so it will not be able to attract that much. It will be weak attraction. So if you go down the group, the electronegativity decrease. Then we'll talk about electron gain enthalpy or ionization enthalpy. What is ionization enthalpy? Ionization enthalpy is nothing but energy required to take out one electron, right? You have to pluck one electron from it. So if you see the lithium, the energy required is more. Why? Because this electron is tightly tied to lithium because the distance between this electron and the lithium nuclei is less. If you talk about cesium here, so this extra electron which we have here, external electron, it is a little lessly tied to cesium. Why? Because the distance between the electron and cesium is cesium nucleus is more, right? So this can easily come out, and this will not be able to come out easily, the dot, and this will easily come out because the distance is less. So the moment you go down the group, the energy required to pull electron will be less, right? Because see, cesium, it's easy to take out an electron. Lithium is difficult to take out an electron, right? So the energy required is more, energy required is less, more to less. So the moment you go down the group, the energy required is less, right? Ionization enthalpy. Same thing is for electron gain enthalpy, where you have to gain one electron. And if you talk about metallic and non-metallic character, we have the similar trend we can explain based on the size of the. So we have seen this in the periodic table chapter where the elements in the groups and periods, they show definite trends, right? Similarly, if you talk about the group 1 and the group 2, right? This is group 1 and this is group 2 elements. They also show a definite trends actually. So we'll talk about these trends, right? So they show a regular trend in physical and chemical properties are increasing in atomic number, and we'll discuss this trends in this following buckets: electronic configuration, atomic and ionic radius, ionization enthalpy, hydration enthalpy, oxidation state, metallic character, physical properties. In physical property, we discuss about photoelectric effect, density, melting and boiling point, softness of matter, and we'll also discuss chemical properties. So we'll discuss all these things. We'll discuss the trends in all these things for alkali metal now, and we'll also discuss the similar stuff for alkaline earth metal also once we are done with this. So let's discuss all these things for alkali metals. The first is the electronic configuration. So if you see the electronic configuration I told was of the pattern NS1. So here if you see all the alkali metals, if you see the lithium, the electronic configuration is 1s2 2s1, right? 1s2 2s1. So it is NS1 pattern. Sodium, if you see 1s2 2s2 2p6 3s1, right? 1s2 2s2 2p6 3s1. So if it is nothing but this guy, NS1 formula. Same thing, potassium also, if you see, it's all are NS1 pattern, correct? This is the general trend for electronic configuration for alkali metals. It is NS1, correct? Group 1. Let's talk about the atomic and ionic radii. So you have seen that the atomic and ionic radii, if you see, if you go down that the group, the atomic and ionic radii increase, right? And that's why, and if you go in the period, in a given period, the atomic radius decrease, right? It decrease in this side or increase in this side, right? So increase. That's why if you see they are little big ones. The alkali metals are little bigger. Yeah. So if you compare with the alkaline metals, it will be somewhere here, and this is alkali, it's alkaline. So they are a little bigger. We will discuss this when we talk about the alkaline metal. So if you see by lithium, then sodium, the size increase, the shells increase, potassium all the more increased, rubidium all the more increased, cesium all the more, francium all the more. And if you remember this chart, right, you will be able to understand 95% of the concepts on the properties of alkali and alkaline. Just remember this chart, and the moment you go down the group, just remember this. The lithium has, you see the shape of lithium, it has the configuration was 1s2 2s1. So s1 has two electrons, and then the second s has 1 electrons. This one, if you see, 1s2 and then 2s2 2p6. So the second one has 8 and the third one has 1 electron. The moment you go down the group, the number of shells increase and the size increase. If you just visualize this in your mind, you should be able to solve maximum questions with the fact that you understand the concepts, right? If you go down the group, the size increase. Why the size increase? Because the shells increase. So with this, if you see, this is the data we have got for lithium. The metallic radius is 152 picometer. For sodium, it increased to 186. For potassium, it's all the more increased to 237. Then for rubidium, 248, right? Again, you don't need to remember this data. Data is not required. Just understand the concepts. The moment you build on the group, the cells increase and the size increase, right? And this size has a critical role to play. There's other properties we can also explain using this behavior. We'll show you how. Let's talk about the ionization enthalpy. So what is ionization enthalpy? Ionization enthalpy is nothing but the energy required to remove one electron from atom, right? You see, it's nothing but energy required to remove electron from atom in the gaseous state or molecule. So if you see the trend we have learned, this is the trend. To explain this trend, let me remember this figure. This is something which I told you. If you remember this figure, you will understand most of the questions. So as you know, the size is increasing, right? Now understand this, if the size is increasing, what will happen? See, if the size is increasing, the control of the neutrons on these electrons will decrease, right? Because if you see, this is less controlled, this electron is less controlled, this is more controlled because it's very near to electron. So it is a very good example is if you are staying with your parents, you are more controlled, right? They control your activities, they control what you eat, what you read. But let's suppose you are in a vacation or a school trip, your parents are not with you, so the parents' control is less, right? Similarly here, the nucleus is very near to electron. So this electron is more controlled by this lithium nucleus. But in this case, this electron is not controlled properly by Frankie. So this guy will not be so comfortable in going out. Why? Because this lithium is controlling this. But this guy, if you see, is easily go out. That's why there is a difference in the dot. Dot means little reluctant to go, and this means it can easily go, right? Because this is not controlled. Since this electron, francium electron, is not controlled properly because of the distance, this can easily go out. So since this can easily go out, the energy required to pluck out one electron from francium is less, right? But since it is very much tied to lithium, the energy required, I'll write less energy required. Here if you see for the lithium or sodium also, the energy required is more here, right? So here more energy is required, correct? So if you see in this case, very less energy is required, here very high energy is required to pluck electron. And then we have first ionization energy, second ionization energy, the energy required to pluck first electron, second electron. We have discussed this in the past few slides, but past chapter, but again I am repeating it. So if you see here, the energy required is less, right? the energy required is more. Since more energy is required, the ionization enthalpy is more. Here it is more. Since the less energy required, the ionization enthalpy is less, and that is the trend we have. The moment you go up the group, the ionization enthalpy increase. The moment you go down the group, the ionization enthalpy decrease, right? Because the less energy is required to burn. So if you just remember this figure of the size of various atoms, you can easily tell the trend for the ionization enthalpy. Same thing, let's talk about the hydration enthalpy. What is hydration enthalpy? The moment you think of hydration, think of water, because hydro came from water, right? So you dip something in water and then some energy is released, and that energy is nothing but hydration enthalpy. So if you see my cobalt chloride in the anhydrous form is blue, the moment you put in water, the color change, it becomes red, and it absorbs 6 water molecule per mole of cobalt chloride. Correct? The moment you think of hydration enthalpy, think of hydra. Hydra means water. That means energy released when 1 mole of substance is dissolved in large amount of water. Correct? The example when I gave was a cobalt chloride, which was blue in color. The anhydrous form, the moment you put in water, it becomes red in color. It absorbs water. So we have to find the trend for this and understand that it's always negative. Why? Because energy is released in this case. Why? Because the bonds are formed, it becomes more stable. The moment you put water in this anhydrous stuffs, more and more bonds are formed and the energy released. And as I told, energy is released when things becomes more stable. So I can say that this is more stable. Now the logic is, smaller the ion, the more is the extent of hydration. Please understand this. So here also, if you see, the hydration depends on the ion size, right? So again, if you have the structure in mind, maybe I'm not able to draw it properly. Yeah. So the smaller the ion, the more is the extent of hydration. And why? Because smaller is the ion, it can absorb water molecules. So here also, if you see, since my lithium was smaller in size, as we have discussed, right? Lithium is smaller in size, sodium is a little bigger. So lithium plus will have maximum degree of hydration. If you see, that's why LiCl, if you see, it generally exists as hydrated salt because it has tendency to absorb water. Correct? So here also, based on the size, you can tell that which one has more tendency to form hydrated salt. And if you see the data we have got, we don't have to remember this, but you see the lithium has the maximum the hydration enthalpy minus 506 kilojoule per mole. If you go down this side, right, if you go down, actually the value is decreasing. The next is the oxidation state. So as you know, all the alkali metals, they have strong tendency to form +1 oxidation state. Why? Because you see they are more stable. Na plus is more stable. Why? Because Na has, if you see the electron configuration, 1s2, 2s2, 2p6, 3s. One extra electron it has. If it lose one electron, it will become stable. So they have tendency to form Na plus always. Correct? Because they want to become stable. So it has generally oxidation state of +1. Generally, 99% case. It will never have, or very rarely will have +2. Why? Because the second ionization enthalpy to lose second electron will be too high, because there won't be any interest for sodium or lithium to become stable. For example, sodium, if you take, it has one extra electron in the outermost shell. So it has one reason to lose electron, because the moment it loses electron, it will become stable. So sodium will want to become Na plus. Right? Once it has become Na plus, it is all stable now. It has electronic configuration almost similar to the noble gas. So it will not have any reason to lose another electron. So first ionization energy required is less, but the second will be very, very high, because sodium will do his best to make sure that the second electron is not lost. Because the moment second electron is lost, sodium will lose its stability, right? Just to be stable, sodium will happily lose one first electron, but second electron will not lose so easily. Correct? So the second ionization energy will be very, very high, and that's why the oxidation state for sodium in most of the cases +1. Correct? So that why sodium 2 plus rarely, I think it doesn't exist, actually. It doesn't exist. Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.